Now, let's discuss some limitations of the current approaches. Let's take the running example of affect detection. First, let's start with unpacking the detector development process. In a standard machine learning workflow, we start by collecting sample S from a probability distribution P. For instance, pairs of images and annotated affective states. Then we choose a model class H, let's say a set of neural networks. We then find a model in this model class which has the lowest prediction error on sample S. Lastly, and this is particularly important for our discussion, we estimate the true error of this model for any future data by testing it on new data that is also drawn from P. This methodology is justified by the fundamental theorem of machine learning on generalization. In simple terms, no matter how complicated the distribution is, for a reasonable model class, if we have enough data, then for any model, the error on current data is a close approximation of the error in the real world. Simply put, if a model does well on the data in hand, it is expected to do well on any unseen data in the future. While this approach may work well for predicting, say, a city's weather tomorrow, it falls short in serving diverse student populations, especially those who were under or unrepresented in the sample S. As reported by Packett and colleagues in their recent review of papers from educational data mining, student population information is often not reported with generalization estimates, making it especially hard to contextualize models. It reminds me of the quote by George Box: "All models are wrong, but some are useful." The question that is often ignored is useful for who? Are the models disproportionately useful for some students or populations over others? By design, most machine learning models are optimized for the majority population because of its focus on reducing the overall error. This leads to bias towards those who do not look like the majority population. There are several reasons for why this happens. The data collected may be less accurate for some groups. For example, earlier cameras were designed to bring out high contrast for white skin color. Or the construct of interest may look different in different subgroups. For example, cultural differences in expressions of emotions. Or some groups may just be hard to predict. For example, students wearing niqab. Identifying this serious issue, as mentioned earlier, several recent research projects have examined bias in algorithmic systems in education. However, the focus has mostly been on investigating bias in predictive modeling, particularly in downstream stages like model development and evaluation. While this is an important step in the right direction, I argue that the issue of bias arises well before the actual model development. And the current emphasis on downstream stages will limit the progress towards equity in adaptive learning systems if we don't broaden our search. It is important that we pay attention to those aspects that closely design and shape the adaptive decision-making, but are often obscured in the evaluation of bias in an algorithmic model. Data collection methods and system design directly impact modeling efforts. Moreover, theories impact system design, data collection, and algorithmic design. letting an algorithmic model perpetuate an upstream bias in its discriminatory decision-making may further harm the sensitive groups, leading to outcomes that falsely confirm the upstream bias. Studying upstream bias is important not only because it could form a basis for bias in an algorithmic model, but also because it could lead to direct discriminatory behaviors in an adaptive system. For example, an affective intervention based on a biased affective theory. Let's take theory, for instance. Theory is an important upstream source because it closely influences several aspects of adaptive decisions, including the conceptualization of a construct, like affect, the interpretation of student behaviors, maybe clickstream in an adaptive system, and the construction of variables in the modeling. What kind of features may go into this model? And lastly, the design of the interventions in adaptive systems. What would a system do, for instance, if a student were to be detected to be frustrated? An upstream bias in theories can manifest itself in a biased decision, for example, culturally irrelevant rewards as extrinsic motivators, or a biased data collection method, for example, a choice of culturally irrelevant affective states to collect data for. It can also influence the decision-making of an adaptive systems more directly. For example, theory-driven rules of affective interventions that are culturally insensitive. Or it could indirectly induce bias through algorithmic models used in them. For example, influencing a biased choice of predictors for boredom detection. In the later cases, upstream biases, for instance, a theoretical bias, could be a root cause of the downstream biases introduced at different stages of algorithmic modeling. Like before, let's pause here and take a minute to revisit the example of the predictive model that we chose before and reflect on the potential sources that can lead to biases in them. Try to be as specific as you can. I'm hoping that this exercise will give you an opportunity to reflect on specific aspects that shape automated decision-making that may or may not be most obvious at the start. And as before, this would be a discussion prompt, so please use your computer to write down your answers.